Okay, so today we're going to look at properties of determinants. This is in section 3.2. So what happens when you do some operations to a matrix? What happens to its determinant? So let's first calculate this matrix A. So what is the determinant of that matrix? So what is it? 0 times 2 minus 4 times 1. So that determinant is going to be a negative 4. Okay, so what happens when we interchange or swap a row? So if I take this matrix 0, 4, 1, 2, and I swap the rows. So I make row 1 now becomes my row 2, and row 2 is going to become my row 1. So it's going to be 4, 2, 0, 1. So what happens? So let's call this now matrix B. So what happens to the determinant of matrix B? Okay, so that's going to be what? 4 times 1 minus 0 times 2. So that determinant is going to be a 4. Okay, so if you interchange or swap a row by those operations, okay, so this is theorem 3 in your book, I believe, if I can remember. So theorem 3 here, if you interchange or swap the determinant of your new matrix is going to be the negative version of the determinant of your original matrix. So if you interchange or you swap. Okay. All right. So scaling. So what happens if we scale our original matrix? So what does that mean? So multiply by something. So, I don't know, let's just multiply the second row by half. How about that? So second row by half, and that becomes my new row 2. Okay, so what happens here? So it's going to be 0, 1, and then this is going to be what? 2, 1. All right, so what happens to the determinant? So let's call this determinant B again. So determinant of B, so that's going to be 0 times 1 minus 2 times 1. So what happens there? So I basically multiply the determinant by that scaling factor. So the determinant of B is going to be the same sign. So whatever the scalar is times the determinant of your original matrix. All right, replacement. So like if you do a row operation, so replacement, so maybe multiply the first row by 2 or negative 2 and add it to row 2, or something along those lines. So that is what row replacement means. So negative 2 times row 1 plus your row 2. All right, so what's going to happen there? So this is going to be 0 times 1. This is still going to be a 4. And then this is going to become a 0. All right, so what happens to the determinant? All right, so what happens to determinant B here? So 0 times 0 minus 4 times a 1. So that's what? Negative 4. So those are going to be the change. So if, so they don't change. So they stay the same. So if we are using replacement, so if we replace a row reduction here, then the determinant of my new matrix is going to be equal to the determinant of the original matrix. Okay, so let's apply this here. All right, so if I want to compute the determinant here, we can row reduce, remember, and if we get all of these to be zeros, what can we do? We can then multiply, the diagonal, right? So that's what we're going to work on right now. Okay, so if we do that, then what are we going to do? So determinant of A Okay, so what could we do? So we could do some replacement. Is the replacement going to change anything to my determinant? It's not. So what could we do? We can multiply 2 times row 1 plus row 2, replace it with row 2. And then we could do what? We could just add those, right? So, or just subtract those rows. So we could say row 1 plus your row 3. And that becomes my new row 3. So what's going to happen here? So 1, negative 4, 2, 0, 0, negative 5, and then 0, 3, 2. Okay. Alrighty, so what about this next one? So what could I do? So could I interchange these right here to get a number there and all zeros at the bottom? So I can interchange. So if I interchange, so I'm going to swap row 2 and row 3. So when I do that, what is going to happen to my determinant? So it's going to be an opposite sign. So I need to take that in consideration when I'm doing my determinant. So I'm going to make a little negative on the outside. So we'll have 1, negative 4, 2, 0, 3, 2, 0, 0, negative 5. So now the determinant of A is going to be equal to the negative version of then all these multiplied. So 1 times 3 times negative 5. So the determinant here of A is going to be equal to A positive 15. Okay. All right, so I'll take a second to answer 2 and 3 for me. Okay, so here you should get a negative 88. How did I get that? So first things first is that I took half of this row 1. So I'm taking half of this row 1. So what am I going to do when I take the determinant of this? Even though that my scalar is half, it's actually going to multiply by a 2 on the outside there. Okay, because remember, you're multiplying the determinant of the original matrix. So if you go back up here and look at this, if you do the determinant, it's going to just be the reciprocal of my new matrix, right? Okay. All right, so then I just do some replacements in my next step here. So I multiply the first row by negative 4 and add it to row 2. And then I multiply the second row by the first row by 3 and add it to the last row. And we get that. So I don't have to do anything to the determinant there. All right, so same thing here. So I'm going to multiply by this one by a fourth. So when I multiply by a fourth, I'm actually going to have to multiply my new determinant when I take the determinant of that matrix by 4. This is just a replacement, so I don't have to do anything. All right, so then I can see that I can interchange these rows, so I can swap them. So when I do that, I need to multiply my new matrix by a negative. So these are all the values that you need to multiply together before you can find the determinant. Okay. All right. So, I want you to try to do example 3 for me, and that's the one I want to see when you upload it today. All right, so properties. If A is an n by n matrix, then the determinant of A transpose is going to be equal to determinant of A. So let's look at an example here. So if I have a matrix A that is an n by n, so square, I don't know, let's call it 6, 1, 3, and 2. So what is A transpose here? So A transpose would be what? 6, 2, 1, 3. So what is the determinant of A? So determinant of A is going to be what? 6 times 2 minus 3 times 1. So that's 12 minus a 3, which is a 9. The determinant of A transpose here is going to be 6 times 2 minus 3 times 1, which is also a 9. Okay, so this is, I think, theorem 5 in that book. Okay, so those are, if A is an n by n matrix, so it's got to be a square, then those two things are going to be equal to each other. All right, if A and B are n by n matrices, then the determinant of AB is going to be equal to the determinant of A times the determinant of B. So I think if that was theorem 5, I think this is theorem 6. All right, let's call A my my original one. B, I don't know, let's call it something else. So let's just change a few numbers. 4, 3, 1, 2. Same kind of concept. All right, so if I multiply these two together, so if I multiply A times B, I'm going to get what? 6 times 4 plus 1 times 1. So I'll get what? 25. And then I'll get what? 6 times 3 plus 1 times 2. So that is a 20. All right, and then I'll multiply. So 4 times 3 plus 2 times 1, which is a 14. 3 times 3, which is a 9, plus a 2 times 2, which is a 4. So that's what, 13? All right, so the determinant of this matrix AB is going to be what? 25 times 13 minus 14 times 20, which is 45. Okay, so what is the determinant of A here? So let's look here. So determinant of A is going to be, we already found it, right, which is 9. Determinant of B is going to be 4 times 2, which is an 8, minus a 3, which is a 5. So 9 times 5, which is also a what? 45. So this is theorem 6. So the determinant of A times B is the same thing as taking the determinant of A and multiplying it times the determinant of B. Okay. All right. Y'all have a great day.